Good morning. This is P. Venkata Mahesh, Assistant Professor in Mechanical Engineering Department, Institute of Aeronautical Engineering. As we discussed in the first lecture, we have a few topics in this Applied Thermodynamics for third semester Mechanical Engineering students. In that, one topic, as we have discussed, is the refrigeration. So, in this class, we will see the introduction to the refrigeration. Now, coming to the definition of refrigeration, what is refrigeration? It is the process of removing the heat from a confined space so that the temperature in the confined space is maintained less than the atmospheric temperatures or the surrounding temperatures, and as well as to maintain it at the same temperature. So, that is the definition of the refrigeration. See, if you see, these are the few applications of the refrigeration. This is a confined space inside the truck. This is the confined space inside a storage room, and this is the confined space in a refrigerator. So, from these examples, you can understand what is the application of the refrigeration. It is to maintain the food materials at lower temperatures and to transport the food materials from one place to another place, and at the storage can be a huge one like this storage plant, or it can be a refrigerator for domestic purpose. So in this way, the refrigeration is playing a vital role in the modern life of human society. Now, coming to the refrigeration, where it started in early 1800s. Okay, in early 1800s, they in US they started harvesting ice. Okay, harvesting ice means they will. During winter seasons, the temperatures will be very low. That the top surface of the river will be covered with ice. And what they will do, they will cut the ice into pieces and they will transport those pieces to the storage rooms, and this ice storage will be throughout the year. So that they have constructed big storage places where they can maintain this ice for throughout the year, and then they will transport this ice to the places where it is required to maintain the food materials. So this is the starting point of the modern way of using the ice for preservation of foods. Now, coming to the mechanical refrigeration systems. So we have three types of refrigeration systems. One is non-cyclic refrigeration systems, and the second one is cyclic refrigeration systems, and these are the modern refrigeration systems. So in cyclic refrigeration systems, we have non-cyclic refrigeration systems, we have refrigeration by ice, refrigeration by evaporation, and refrigeration by dry ice. And in cyclic refrigeration, we have air refrigeration cycle, vapor compression refrigeration cycle, as well as vapor absorption refrigeration cycle. And in the other refrigeration systems, we have thermoelectric refrigeration, steam jet refrigeration, vortex tube refrigeration, and more, so on. We'll confine our discussion with to these 9 process, but recently there are many other refrigeration systems, process like magnetic refrigeration systems and so on. Coming to the non-cyclic refrigeration systems, the first one, as I said, it is a ice refrigeration. So how this ice refrigeration happens? So what we can do, as we have seen in the previous slide of ice harvesting. So this ice refrigeration, what we can do, we can keep the ice in this tray. Okay, the ice in this tray, if I keep as we all know, the latent heat of ice is very high. It is 335 kilojoules. Okay, latent heat of ice is 335 kilojoules per kg. Now, this latent heat, if I keep the ice there, what happens? It will take the heat from the surroundings. Okay, it will take heat from the surroundings, and what will happen? It will try to melt. Okay, because the surrounding temperatures are higher than the ice temperature. What will happen is the ice will take temperature from the surroundings and it will start melting. And in the process, what happens is, because it is taking heat from the surroundings, the surrounding air will get cool. Okay, it will get cooled, and as the air gets cooled, the density of the air will become high. So when the density of air becomes high, it will go down. Okay, it will go through these storage materials. Okay, and because of that, now this cold air replaces the hot air inside this storage place. Now this hot air, because it is lighter than this cold air, it will go up. In this way, will create some convection currents. Okay, this is called convection currents. The heavier cold air will come down and the light hotter air will go up. This is called the convection currents. And because of these convection currents, what happens is, the food materials here, they will be preserved. They can be preserved at lower temperatures for fresh for longer time. And this cooling process will continue till the ice in the tray melts completely. And when the ice is completely melts, we have to replace that water and we have to place the ice again. So this is the ice refrigeration process. Next one is evaporative refrigeration process. So this is a very olden refrigeration process, rather than it is a natural process that happens. So from the very olden days in India, they use the earthen pots. So the earthen pots, what happens in the earthen pots is, there will be some holes, very minute holes will be there in the earthen pot, which cannot be seen by naked eye. And through this holes, porous holes, the air will try to come out. And the surface of that air, say suppose the pore is like this, and the surface of this the liquid inside this air, what it will happen is, this will take heat from the surroundings as well as from the water, and this fine layer will get evaporate. Okay, when this happens, the temperature inside the air, inside the pot, the temperature inside the pot will go down, and as well as the surrounding temperature also will go down, and this liquid layer will get evaporate. So this is a natural process of the natural process that is being used from very olden days, and this is called the evaporative refrigeration process. And here the heat removed from the evaporation of water is partially from air and water, that we have to remember. So the air inside the water inside the pot will give some air, some heat, and the air surrounding also will give some heat, will take some heat, and because of that, the surface water will get evaporate. So in the process, so for this to run properly or to effectively cool, the air breeze should be there continuously. So that means the pot should be exposed to air which is moving. It should not be a stagnant air. If air is moving freely, in such cases, what will happen is, the inside water, in the water inside the pot can be cooled continuous. And There are many other applications where we can see this evaporative refrigeration, and the evaporative refrigeration can give as a temperatures 5 to 15 degrees less than the surrounding temperatures. Okay, the 5 to 15 degrees less than the surrounding temperatures. So some other examples of this evaporative refrigeration where it happens is the flowing water. So the flowing water in a river, what happens is, again the top layer will get evaporate, and the air the air will give some heat, and the water below it will give some heat. Because of that, the top surface will get evaporate, and because of that, as the say suppose this is the uh, river, and the air goes like this. So if the air goes like this, we can feel the cool breeze near the lakes, rivers, etc., and the water inside the river will become cool. Okay, it will be cooler than the surrounding temperatures, as well as we get the cool breeze from the water bodies. And the other one is, we our human bodies have some sweat pores, and as the sweat as the body feels the temperature is little higher, what it will do, it will eject some sweat, and that sweat, the surface of the sweat will get evaporate, and in the process what will happen is the body will get cool. Okay, the body will become little colder than what it should be. And the other where other place where it is used is the desert bags. So in deserts, what they will do, they will carry some bags which are having the porous uh, porous cover, the bags with the porous cover, and inside that water will be there, and the water will get this evaporative refrigeration, and the water remains cool inside that bag. So these are the few examples where this evaporative refrigeration happens. And artificial, this so far we have seen is the general day-to-day things. Now here we are seeing the uh, application in industry. Okay, here we can see that the compressed air is thrown through this nozzle. As the compressed air thrown to this nozzle, what here the area is decreasing. Okay, this is a convergent nozzle. Because of that, what happens is the velocity here will be very high. So velocity, as velocity is very high, the pressure will be little lower, and because of that, what happens is the water also will be taken inside. And since the pressure is too high here, and the what happens is, here the pressure will be too low, and of the order of 5 bar. See, at the inlet the pressure is 10 bar, and at this place the pressure is 5 bar. And because of that, the atmospheric temperature is 1 bar, and the atmospheric pressure is 1 bar, and the pressure here it will be 5 bar. And uh, uh, so what happens is, the air will take heat from the surroundings, and here some low temperature will form. And if I supply some water here through this wall, this water will become snow kind of particles, snow particles. It will become snow particles because the temperatures will be very low. It can be even 0 or less than 0 temperatures because of this pressure differences. So this evaporative refrigeration is used where, when we need an artificial snow to be generated. Say suppose in our movies and all, they will use this kind of artificial snow preparation techniques. And the next one is refrigeration by dry ice. So what is this dry ice called? So the dry ice is nothing but the the solidified carbon dioxide. What is how the solid carbon dioxide solidified. Okay, that is the first thing. Now the first thing is it is compressed to a pressure of 69 bar. The carbon dioxide is compressed to a pressure of 69 bar, and at that pressure it is cooled to 28 degrees centigrade. Okay, the CO2 is compressed to 69 bar and as well as cooled to 28 degrees centigrade. And with this, what will happen is the CO2 gas will become a completely liquid. Okay, the CO2 gas will become completely liquid. Now this liquid, when it is expanded to 1 bar, so the liquid carbon dioxide is expanded to 1 bar from 69 bar. In that process, what happens is we'll get solid carbon dioxide and the temperatures will be as low as minus 78.5 degrees centigrade. Okay, now the temperatures are very low, like minus 78.5 degrees centigrade, and if I can keep this in some insulated container, I can keep so the things for very very low temperatures, and especially the solid CO2, it will come directly converted to vapor. Okay, there will not be any liquid state. Instead of that, when this the temperature increases, the solid CO2 directly becomes vapor and it will produce cool atmosphere surrounding to that. So since there is no liquid state, only solid to vapor, the eyeballs which are used for surgery, they are preserved using this dry ice. Now we have seen some non-cyclic refrigeration techniques, and there are some drawbacks for this non-cyclic refrigeration techniques. One drawback is the refrigeration space. So okay, the refrigeration space, temperature of this refrigeration space cannot be maintained at a given or required temperature. Arbitrarily, because of the cooling, refrigeration process, some temperature will be attained, but it may not be to the required thing, and we cannot control it to the precise. So that is the main disadvantage of this non-cyclic refrigeration techniques. And there is no working substance. Okay, the working substance is not there. So this is to produce the refrigeration effect at required temperature. Okay, so we are not using any working substance that can be maintained for at a given temperature, and one has to replenish the ice periodically. So the dry ice will get evaporate. I have to change this. We replace with fresh dry ice, and the normal ice will get melts, and then again I have to replace the ice. In this way, I have to replace the ice periodically. Otherwise, the refrigeration process cannot be refrigeration temperature cannot be maintained continuously. So these are the non-cyclic refrigeration process. Now coming to the cyclic refrigeration process, we have air refrigeration cycle. So this is the first one. In air refrigeration cycle, what happens is we use a compressor. Okay, we use compressor, we use a turbine, and we use the two heat exchangers. And with this kind of setup, what we will do, we will try to maintain one place hot. Say suppose this is the refrigerator. Okay, this is the refrigerator and this is the surroundings. Okay, now the refrigerator is maintained at temperatures well below the surrounding temperatures using this cyclic process. Now how again what happens is, as here the pressures are very low, so the low pressure air will take heat from the cold reservoir, and this hot air will be compressed, and when the pressure increases, what happens is automatically the air will reject heat to the atmosphere, and even though the atmosphere is having temperature higher than the cold reservoir, this cyclic process can extract heat from the cold reservoir and supply it to the hot surroundings. So this is the one process, cyclic process, and it is called the air refrigeration cyclic process. We will see the what is the performance and all in the further coming classes. Now here the compressor will require some work input, okay, and part of that work input is supplied by the turbine, okay, part of that work input is supplied by the turbine, and remaining will be supplied by some motor or something, okay. So here part of the work is supplied by the turbine and part of the work is supplied from the motor. So this gives the net work which is supplied by the motor. Now with this network, what is happening is the temperature, the heat is taken from the cold atmosphere or the cold place, storage place, and it is given to the hot surroundings. So the cold places are maintained at lower temperatures to the lower temperatures than the surrounding temperatures, and this can be a continuous process. As long as the work is given, the temperatures here will be low and heat will be rejected to the surroundings. And here one advantage is you can define what is the pressure here, to what extent I want to compress this, and to what extent I want to expand this air inside the turbine. So we can adjust this compression, the pressures of the compressor and turbine, because with that what we can do is how much heat we can extract from the cold and how much heat can be supplied to the hot reservoir, they can be regulated. So this is the one advantage of this cyclic process. In cyclic process, we can control the temperature of the cold surface, cold storage place, by controlling this compressor and turbine pressure. Now next one is vapor compression refrigeration cycle. So this is another cyclic process. In this, what we are doing is we are replacing the turbine with an expansion valve, okay, and we are supplying the entire work to the compressor. Previously part of the work is supplied by the turbine, but here the entire work we are supplying to the compressor. So one can ask, sir, why we are going for this? There the turbine is giving some work, here no work is supplied by the expansion valve. Why we have to go for this kind of setup? Now here if you see, the working media is a fluid, okay. The fluid is the working fluid, okay. The fluid, the liquid is the working fluid here. Now here what happens is the liquid and traces of vapor will get evaporated in the evaporator, okay, and here low pressure liquid will be there, low pressure liquid. So the low pressure liquid, what will happen is when the pressures are very low, the boiling point will be very low, okay. The pressures, as the liquid pressure goes down, the boiling point of the liquid goes down, and because of that what happens is it will take the heat from the cold storage place and it will get evaporated. And when this vapor is compressed in the compressor, what happens is it will, the boiling point of this vapor will increase. Okay, the vapor temperature increases tremendously, and the heat will be rejected to the reservoir. And now here, coming to the point of turbine, again this, here we are using liquid, there we are through the turbine the air is passing, and air can produce a lot of work, but the liquid, it cannot produce lot of work, and the turbine also will get spoiled, and the space occupied by the turbine will be very high, because the density of the liquid is very high as compared to that of the uh, air. So because of that reason, the space occupied will be very high and work produced by the liquid is very low. So what we are doing is we are replacing the turbine with an expansion valve, and here again we are using the compressor, and the space reduction and the maintenance of the turbine, all those things will be eliminated, and the net work required by the compressor is directly supplied by the motor. So this is the vapor compression refrigeration cycle. So you can use normal water in this, or you can use ammonia in this, or any other liquid which can be converted into vapor, like that we can use. So this is about the vapor compression refrigeration cycle. So the next one is vapor absorption refrigeration cycle. So in vapor absorption refrigeration cycle, the compressor is replaced by a component called thermal compressor. So this entire this part is doing the work of the mechanical compressor that we have seen in the vapor compression refrigeration cycle. Remaining parts are the same. This is the condenser, where the heat is rejected to the surroundings, and this is the evaporator, where the heat is taken from the cold storage place, and this expansion valve in which the temperature, the pressure of the liquid is reduced. Okay, so this is the layout of the vapor absorption refrigeration cycle. And what is this thermal compressor? So here inside this thermal compressor we are using another liquid, so to get this compression happens. So how this happens, here we can see. Now here the expansion valve is there, and here we are having a pump. Instead of there, we are compressing the vapor. Now here what we are doing, we are pumping only liquid, and here this is a generator and this is absorber. Now what is this generator and absorber? So here so the liquid absorbing liquid will be coming, and this liquid, what it will do, the whatever the refrigerant is there, it will get absorbed inside this absorber into this liquid. Now this liquid is called this is here what is happening is it is absorbing the so-called refrigerant inside from the circuit, and here we will get very high concentration of the refrigerant inside this. Now what happens is this refrigerant as well as this liquid, so okay, this absorbing liquid and refrigerant both will be pumped to the the generator. So here I have a strong solution of the refrigerant. So the strong solution and weak solution. What is the meaning of the strong solution and weak solution? The strong solution means the say suppose the lithium bromide and ammonia two liquids will use in vapor refrigeration cycle, or ammonia and water can be used. So here the refrigerant, what it will do here is, so here the refrigerant will get absorbed inside this liquid. When it is pumped to higher temperature, higher pressures, what happens is the boiling point of the refrigerant will increase. So the boiling point increases, and because of that, what happens, it will become vapor, and here the refrigerant will be supplied to the this condenser, okay, to this condenser, and so because the refrigerant is leaving the generator, here will again form weak solution. The weak solution is expanded into this expansion valve, and again here the liquid will absorb the refrigerant, and it will become a strong solution, and again it will be pumped to the generator. Okay, so like this the weak and strong solutions of the refrigerant will be there inside this thermal compressor, and in that way what will happen is it will maintain the storage room at lower temperatures and less than the temperatures of the surroundings. So here what is happening is we are supplying less work. Instead of less work, along with less work, what we are doing is we are heating this generator. Okay, so in this liquid combination, one liquid will have higher boiling point, the other one will have lesser boiling point, and the lesser boiling point will be the refrigerant, and the higher boiling point will be the absorbing liquid. So the lesser boiling point refrigerant will get evaporated in the generator as we supply heat, and it will go to the condenser. So in this way this thermal compressor works. Now coming to the modern refrigeration techniques, one is the steam jet refrigeration cycle. So the steam jet refrigeration, not cycle, it is a refrigeration system, the steam jet refrigeration system. So here also it is a continuous process, but it is not a cyclic process. Okay, so what is happening here we have to see. Now here the here this is boiler, and this boiler is water is expanded through this nozzle. So when the water is expanded through this nozzle, what happens is the velocity will be very high. So this high velocity vapor, what it will do is it will go through this convergent divergent section called ejector, and along with that what it will do, it will take some vapor from this flash chamber. Okay, now here since here the velocity, the high velocity fluid is going, so here some vacuum will be formed, and because of that vacuum some the top will become vapor, and it will go through this ejector, and it will get condensed into this this chamber. Okay, so here we are using only water. Okay, here this is boiler. In boiler steam is generated, and the steam is passed through this nozzle, and where the velocity of the steam will be very high, and it will cause some vacuum here. Vacuum means the pressure will be low, so because of that the here water is supplied through the sprinklers, and these particles, the surface of the water particles will get evaporated, as well as the water from the surface of the flash chamber will get evaporated, and this vapor will be taken along with this high speed vapor from the nozzle, and it will go through the ejector, and here as we supply the cooling water, okay, the cooling water is supplied and it is taken out. So the cooling water will take heat from the this steam, Okay, this cooling water will take the heat from the steam and it will give hot water outside. And now here, as the heat is taken by this cool water, the steam is uh, condensed into the what liquid form, and this liquid is again supplied to the boiler. And here, as the water is getting evaporated, what happens is we have to again supply some water. So this is the makeup water, because the level of the water is going down, we have to make up the water. And since here the surface of the water is getting evaporated, what happens is the evaporation refrigeration is being used here. So here what is happening, since the surface of the liquid drops and the surface of this liquid column is getting evaporated, the water inside this drops as well as this inside this chamber will become cool than the surrounding temperatures, and this cold water is supplied to the refrigeration plant or air conditioning plant. And there what it will happen is the cold water will take the temperature of the air, and again that water is supplied through this sprinklers inside this flash chamber. So this is here one cycle is there. The cold water is going to the refrigerant place or air conditioning place, and the hot that will take the heat from the air, and that hot water is sprinkled in the flash chamber. So this is one cycle that is happening here. The another cycle that is happening here is the from the boiler hot steam is supplied through the nozzle, and this high velocity steam is taking this steam as well as with that, and here it is getting condensed into liquid, and again this liquid is supplied to the boiler. So this is another cycle that is happening. So here two cycles are there in this steam jet refrigeration cycle. So next one is thermoelectric refrigeration. Now what is this thermoelectric refrigeration? We have something called Seebeck effect. So what is this Seebeck effect is, if two ends of a junction, okay, we have two different conductors are forming a junction, okay, this is one conductor and this is another conductor. Now these two conductors are forming a junction. Here this is one junction and this is another junction formed by these two different conductors. So because of this, what happens is, if this and these junctions are maintained at different temperatures, say suppose this is high temperature and this is low temperature. So when this is high temperature and low temperature, because of that temperature difference, there will be some EMF generated inside the circuit. Okay, so the EMF is generated inside the circuit because of the maintaining the junctions of two dissimilar conductors at two different temperatures. So some EMF is generated. So that is called the Seebeck effect. Now this Seebeck effect is used for refrigeration. How it is used? It is used by Peltier in a different manner. So what he is doing is, he is again forming the two junctions with two dissimilar conductors. Now what he is doing is, he is supplying the electricity here. So as he is supplying the electricity, what is happening is, the temperature of one junction is going down and the temperature of one junction is going up. So this is becoming a hotter junction and this is becoming the colder junction. So this is called the Peltier effect, and this junction will give some local refrigeration effect. So this is the thermoelectric refrigeration system. So what is, again we will see what is happening in this thermoelectric refrigeration system. We are using some electrical energy. Say suppose here batteries are there, and these batteries are supplying some electric current, and this is one conductor, this is another conductor with two different conductivities. So different conductors means the conductivity is different. Now as the conductivities are different and the energy, the electricity is supplied through one conductor, what is happening is one junction will become cold junction, the other junction is becoming a hotter junction, because the electricity is coming through in this direction. Okay, when the electricity is flowing in this direction, this will become the colder junction, and this will be the junction towards which the current is passing, it will become the hotter junction. So here we can heat the things, and here we can cool the things. So both things are attained. So we can, one place we can heat, and the other place we can cool using this thermoelectric refrigeration system. So the next one is vortex tube refrigeration. Now what is this vortex tube refrigeration? So here the high pressure air or compressed air is supplied through the nozzle. So when it is supplied through the nozzle in such a manner that it will cause some what do you say, spiral kind of flow will happen here. Now this compressed air is a little hotter. Now what happens here is the compressed air, it will form spiral and it goes through this nozzle. Now here the temperature is little higher. If I restrict the flow, okay, if I freely allow, it will go directly. If I restrict the flow such that some part of this hot air leaves this space, what happens is it will cause a core, the central core, the central core will be a cold temperature region. Okay, this is the hotter air, it is going in the spiral, and here we are restricting the flow. Okay, we are restricting the flow in the sense we are not allowing the hot air to come out directly. So because of this restriction, what is happening is here the pressure will be high and here the pressure is low. So from high pressure to low pressure, a reversal flow will take place, and this reversal spiral will give the cold, you can say it is a super cooled air that is coming out of this vortex tube. So this vortex tube can give a spot localized cooling effect. Okay, this gives the localized cooling effect, and here since this temperature is taken by this hot air, here we will get the hotter temperature. So one side we are getting hot temperature and the other side we are getting cold air. So this is the vortex tube refrigeration. So what is happening here? We are restricting the flow. If I don't restrict the flow, the hot air will go out freely. But as I am restricting the flow, what is happening here? Here low pressure is there, and here there is a restriction. So because of that, the reversal flow will happen, and the reversal flow goes through the through the central core of this spiral, and the central core will give the super cooled air, and this will give hot air. So this is the vortex tube refrigeration. So with this we are coming to end of this particular session. So here what we have seen is we have three types of refrigeration, mechanical refrigeration systems. One is non-cyclic refrigeration systems, the cyclic refrigeration systems, and the other one is the modern refrigeration systems. So the cyclic refrigeration systems are widely used, and the modern refrigeration systems are still there is some development is going on these systems for using widely. And the non-cyclic refrigeration systems, they are old and traditional systems where the the cold space is maintained at a temperature which we cannot control. The temperature cannot be controlled by us. It will be automatically defined by the temperature of the ice in or the in evaporative refrigeration system also we cannot maintain the particular temperature which we need. So some cooling can be there using this non-cyclic refrigeration systems, but with the cyclic refrigeration systems we can maintain the prescribed or required temperature by adjusting the pressures of the expansion valve and the compressors. Okay, so this is about the introduction to refrigeration. We'll see further in further classes. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.